Hello everyone, my name is Jerry, and today we are going to start off a series of videos on digital systems, the analysis of digital systems and digital systems design. This is video number 1, an introduction and number systems. Alrighty, let us begin. Let us first talk about digital systems. Let's describe it, and let's define the boundaries of a digital system. So a digital system has to have discrete values, and that is important. That is pretty much the whole definition of a digital system. And in our world, the electronics world that we are going to be dealing with, the two discrete values are 0 and 1. And what that means is all other values are not allowed in our digital system. So values such as 2 or 0.5 are not allowed. And so in comparison, an analog system, values such as 0.5, so over here we have an analog system, 0.5 are allowed, 0.25 may be allowed. However, do note that there is one similarity between an analog and a digital system, and that is that both of them can have constraints, they can have boundaries. So similarity is that they can both have boundaries. So in the case of our analog and digital system, let's say our constraint or boundaries is between 0 and 1. So that means in our digital system we can only use the numbers 0 and 1. However, in our analog system we can use any numbers between 0 and 1. So something like 0.25 is legal, and so is 0.5. However, if it's outside the constraint, it's not legal for both systems. So something like 4 is not allowed for both our analog and digital system. However, depending on the system that we're using, the constraint changes. So in our case for the electronics world, using our digital world, our constraint is 0 and 1, and we can only use 0 and 1. However, there is no constraint for the analog world since we change our analog use. So you can have, normally when we talk about analog world, we can talk about voltages and currents, and since there is no practical constraint, you really don't have one. But let's use another example to maybe cement the idea, the difference between an analog and a digital world, or definition. And let's use clocks. So we have an analog clock on the left, and we have a digital clock on the right. So let's focus on the minutes. Okay, now let's draw a minute hand. Let's first draw the minutes in here. So there's going to be 5 minutes from 4 to 5. And then let's draw a minute hand that extends over here. Okay? So in our digital world and our analog world, we have the boundary that it can only be both systems can only take on values between the numbers 0 to 60. So something like 61 is not allowed. And if you think about it, you can't, when you say 61 minutes, that really doesn't make too much sense if you are saying it in the context of saying, oh, it is 12:61. That doesn't make sense. In fact, 60 doesn't even make sense. So we should change our boundary to 0 to 60 non-inclusive, or 0 to 60 non-inclusive for all of you math geeks out there. However, for our digital system, we are only limited to 0 to 60 by integers. So we are only limited from 1, 2, 3, 4, 5 increments of 1. And in our analog world, we are not necessarily limited by that. What I mean by that is, so if we take a look at our digital clock here on the right, we can definitively say that this is 12:30, or the minutes show that it is 30 minutes, right? However, if we take a look at our analog clock, what we can say is that it is definitely between 22 and 23 minutes. However, I can estimate that to be 22.75 minutes, and that is totally legal because it is within our bounds of 0 to 60 in our analog world. And hopefully that somewhat clarifies the differences between an analog and a digital world, or a digital system. Alrighty, now I'm going to move on to numbering systems, and I'm going to use the decimal numbers as an example. So, what that means, first off, with any numbering system, you have a base of n. And in our case, so our example of using decimal numbers, we have a base of 10. And then we have n distinct numbers in our base. So in our case, we have the numbers 0 to 9. And with all numbering systems, we start with the rightmost number, and the rightmost number is the n number to the 0th power, and then once you fill up all the numbers in the n to the 0th power, we add a power to the left of that, so the next one will be n to the 1, and once we fill up all that, we add 1 to the left of that, so that is n to the 2, and we continually do that until we have satisfactorily, or we have filled up all our numbers, so n to the, let's say, 8th power. Okay? So in our case, with decimal numbers, we have the rightmost being 10 to the 0th power. To the left of that is 10 to the 1, and to the left of that is 10 to the 2, and so on and so forth. So if we have a number, say 283, what that means is we have 3 times 10 to the 0th power, we have 8 times 10 to the 1st power, and we have 2 times 10 to the 2nd power. And we can get the number 283 by adding all those powers up, so 2 times 10 to the 2 plus 8 times 10 to the 1 plus 3 times 10 to the 0 is equivalent to saying 283. And that is the same with all numbering systems, so it works with base n, or n being any number that you choose. Alrighty, so now we are going to go and move on to binary numbers. Binary numbers are really important because they are what we are going to be dealing with, because remember how I said in our digital world we're going to be dealing with two numbers, 0 and 1? That is called binary. And it is base of 2, so remember how I said the base of n, there are n unique values. Well, in base of 2 we have 2, 0, and 1, and so as I said before, we're going to be dealing with this a lot in our digital systems and digital systems of design, because this is a language of computers and we use this a lot. So to differentiate binary numbers from decimal numbers, or the numbers that we usually use, we can have two notations. The 0b notation is more programming oriented. So if you were programming in C or C++, when you write your code, you would put 0b and then the binary number, and that will tell the computer that, okay, rather than writing a decimal number, I just wrote a binary number. Another method of telling people that you have written a binary number instead of, say, a decimal number is a subscript. So you write your binary number, which, remember, only contains 0 and 1, nothing else. You have the binary number with a subscript of 2, denoting that it is a binary number and not a decimal number. So let's quickly review again how numbering systems work, and let's use a more specific example using the binary number system. The rightmost digit will be 2 to the 0th power. To the left of that is 2 to the 1. To the left of 2 to the 1 is 2 to the 2, 2 to the 3, and so on and so forth until you have reached the number that you wish to represent using 2 to the n digits. And so that means if you had a number, let's say 1011, what that means is you have 1 times 2 to the 0, you have 1 times 2 to the 1, and you have 0 times 2 to the 2, and finally you have 1 times 2 to the 3. And then you can express that equivalently by adding them all together. So you have 1 times 2 to the 3 plus 0 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0. And the 2 to the 1, the 2 to the n power are not necessary, but I have actually quickly just explained how to convert from binary to decimal. I'll explain it more in depth later in a later slide, but what you basically are saying is that, okay, so since there is a 1 at the rightmost digit, you have 1 times 2 to the 0. And that's how numbering systems work. Now, next slide, I'm going to talk about conversions, and so let's get to that. Okay, now we are going to move on to conversions, decimal integers to binary. And so there are 2 methods of doing that. The first method is dividing by 2, and if the quotient is a whole number, you append 0 to the left of the decimal point, and otherwise you append a 1 to the left of the decimal point. So what I mean by that is, if we have a number, if we have a decimal number, let's say 25, and we divide that by 2, we get a number 12.5. And because the quotient, the 12.5, is not a whole number, we append a 1 to the left of the decimal point. So this is our result. So we append a 1. Then we take that number and we cut off the 0.5 if the 0.5 exists. Otherwise, we just take the number and we do the process over again, 12 divided by 2. And if it is a whole number, in this case it is a whole number, we are going to append a 0 to the left of the previous number, and not the left of the decimal point. So it will be 0 to the left of the 1. And we continue this again, so 6 divided by 2, that is 3, and because 3 is a whole number, we append a 0 to the left of the previous number, which is a 0. And then 3 divided by 2 is 1.5, and because 1.5 is not a whole number, we append a 1 to the left of that. And then again, we take the 1.5, we truncate the 0.5, we ignore it, and then we take the 1 divided by 2, which is 0.5, and because 0.5 is not a whole number, we are going to append 1 to the left of our previous number. And so our 11001 binary is equivalent to 25 in decimal. And to just clarify it a little bit more, I will do another example. So let us convert a number, let's say 56, into binary. We're going to write our results down here. And we're going to add our decimal place right there. So first we do 56 divided by 2. And we get the result of 28. And because 28 is not, it is a whole number, it is not a not whole number, we append a 0 to it, to the left of the decimal point. And then we take that number, we take the 28, and we divide that by 2. And what we have is 14, and because 14 is not a, it is a whole number, we append a 0 to the left of our previous number. Then we take 14, continue this process, divide by 2, which is 7, and because it is a whole number, we add a 0. And then we take 7, and we divide that by 2, and we get 3.5. And because 3.5 is not a whole number, we add a 1 to the left of our previous number, and then we truncate the 0.5, we ignore the 0.5, and continue with our process. 3 divided by 2 is 1.5, and because 1.5 is not a whole number, we add a 1. And then we go back to our number 1.5, we ignore the 0.5, and we continue with our process. So 1 divided by 2 is 0.5, and because 0.5 is not a whole number, we append a 1 to the left of that. So our result, so 56 in decimal, is equivalent to binary 1, 1, 1, 0, 0, 0. Alrighty, I said before that there were two ways of converting from decimal to binary, integer-wise, and so the first one was dividing by 2. The second one is subtract by the largest power of 2. So your first step is to find the largest power of 2 that can subtract from an integer, and then second step is you continually subtract until the value of the decimal is 0. So what I mean by that is, we said before that all numbering systems, you have n to the 0th on the rightmost, and you continually add 1 until you can represent your number. So what we're going to do is we're going to take 2 to the 0 for the rightmost digit, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5. We're going to continually do that. We're going to do 2 to the 5. 6 spots is normally enough, and we're going to convert that into decimal. We're going to convert it into nice numbers right now. So 2 to the 0 is 1, 2 to the 1 is 2, 4, 8, 16, 32. And what we're going to do is we're going to take our number that we wish to convert. So let's say convert 27 into binary. What we're going to do is we're going to find the largest power of 2 from over here on the right that we can subtract from 27. So we realize that 27, the largest power that we can subtract is 16, and then what we get is 11. And so what we know is that there is going to be 1 times 2 to the 4th power, because 2 to the 4th power is 16, and then we are going to see it. Then we're going to ask ourselves 2 to the 7, 2 to the 7, my apologies, 11. So 11 minus what is the next largest number that we can subtract, and in this case it is 8. So 11 minus 8, we have 3. And so what that means is we know that there is 1 times 2 to the 3. And then we're going to continue that process. So 3 minus the next largest is 2, which is 1. So we know that there is 1 times 2 to the 1 power. And then finally 1 can be subtracted with 1, which is equal to 0. And so we see that we end up with a value of 0, and you will always end up with a value of 0. If you don't, then you did it wrong. You didn't subtract by the largest, or you don't have enough digits. You don't have enough powers. So we know that there is 1 times 2 to the 0. So now we can come over here and we can start from the right. And so we have 1 times 2 to the 0. So I'm going to put a 1 in the 2 to the 0 space. We have 1 times 2 to the 1. We can put a 1 in the 2 to the 1 place. And we see that there is no 2 to the 0. 2 to the 2. So that is going to be a 0 because there are we don't have 1 times 2 to the 2. We do have 1 times 2 to the 3, so we're going to add 1 over there. And then finally we have 1 times 2 to the 4, so we can effectively say that 27 in decimal is equivalent to binary of 11011. Okay, so now we are going to focus on fractional decimal to binary. And again, we have two methods. The first method is multiplying by 2. So remember how our first method of integer decimal to binary was divide by 2? Well, for fractions, we multiply by 2. And what we do is, if the number is larger than 1 this time, we append 1 to the right of the decimal point. And in this case, it is to the right of the decimal point, not to the left. Otherwise, we append a 0 to the right of the previous number or decimal point. So let's do an example. Let's do two examples. Let's convert 0.25 to decimal to binary. And so what we do is method 1, we multiply that by 2. And so let's put our result over here, and we have our decimal point. So 0.25 times 2 is 0.5. Because 0.5 is not larger than 1, we append a 0 to the right of the decimal point. And then we take that and we repeat the process, 0.5 times 2. And what we see is that it is 1. Perfect. We append a 1. And our result is 0.01 in binary is equivalent to 0.25 in decimal. And so now that worked out perfectly. However, let's do another example over here. Let's do 0.33 to binary. And what you're going to see is that not all binary fractional decimal numbers can be converted nicely into binary, while all integer decimal numbers can be nicely converted into binary. It is not the same for fractional decimal numbers. So what we're going to do is we're going to stay with our convention. All right, we're going to take 0.33 and let's put our results down here. Result with our decimal point there, and we're going to take 0.33, multiply that by 2. And what we're going to see is that it is 0.66. And because 0.66 is not larger than 1, we're going to append a 0 to the right. We're going to take 0.66. We're going to multiply that by 2. And what we see is that it is 1.32. And 1.32 is larger than 1, so we append a 1 to it, and as previously we take this 1 and we neglect it, and we continue on with the process with 0.32, whatever is to the right of the 1. So we take 0.32, we multiply that by 2, and we get 0.64. And because 0.64 is not larger than 1, we append a 0. Then we multiply 0.64 by 2, and we get 1.28. And so 1.28 is larger than 1, so we add a 1 to the right. And then again, we ignore the 1, and we take what is to the right of the 1, so 0.28. And we continue this process, and we can continue it indefinitely, because we will never have an exact binary representation of 0.33 in decimal. Binary in decimal. We will never have 0.33 decimal in binary as an exact result. So we're gonna say that this is a close enough result to 0.33 in decimal. And of course, you can continue this for as many digits as you want, but I think 4 digits is sufficient. Okay, so the second method is subtracting by the smallest negative power of 2, and that is kind of a mouthful. And so again, with numbers, when you have numbers to the left of the decimal place, it is positive power, so the first digit is 2 to the 0 in our case for binary, 2 to the 1, 2 to the 2. However, as you move to the right of the decimal place, it is negative. So to the right of the decimal place, the first number is 2 to the negative 1, then 2 to the negative 2, and 2 to the negative 3, and so on and so forth. And so what that is equivalent to is 1/2, or 1 to the 2 to the 1, 1 over 2 to the 2, and 1 over 2 to the 3, which is equivalent to 0.5, 0.25, and 0.125. So what we do is we find the we find the largest number that we can subtract by, and we continue to do that. So in our case, let's say we are, so if we convert like 0.5 to binary, we see that 0.5 subtracts with 0.5 really nicely, and what we get is 0.1 in binary is equal to 0.5 in decimal. However, if we have a number that is not so nice, so let's say let's say 0.40, what we're going to realize is that, okay, since 0.40 does not subtract well with 0.5, we're going to add a 0 because there are 0.5s in 0.4, and then we can subtract a 0.25, so 0.4 minus 0.25 is equal to 0.15, so there is 1.25, so we append a 1 to the right of our 0, and then we can subtract 0.125 from 0.15, so 125, and what we get is 0.025, and so we can add a 1, and then we can continually do that indefinitely for however many digits that you want to do. And so that is our answer. So 0.011 is around 0.011 in binary is around 0.4 in decimal, and that is how you convert decimal to binary, decimal fraction to binary. That is a second method. Okay, the previous 4 slides were converting decimal to binary, and finally we are going to convert binary to decimal. Converting binary to decimal is a lot easier than converting decimal to binary, because what we have is, so we are given a number, let's say 1101 dot 001, and so basically what you see is that you just add the corresponding powers of 2. So remember how we said the first digit was 2 to the 0th power, second is 2 to the 1, 2 to the 2, and 2 to the 3 on the left side of the decimal, and then on the right side it should be 2 to the negative 1, 2 to the negative 2, and 2 to the negative 3. Well, what we do is we just take all the places that has 1, and then we have 1 times 2 to the 0, and then we have 1 times 2 to the 2, and we have a 1 times 2 to the 3, and we have 1 times 2 to the negative 3. So we just add all of those together. So in this case, 1 times 2 to the 3 is equivalent to 8, 1 times 2 to the 2 is equivalent to 4, and 1 times 2 to the 0 is equivalent to 1, and 1 times 2 to the negative 3 is 0.125. So when we add them all together, we get 8 plus 4 plus 1 plus 0.125, and that is equivalent to 13.125 in decimal. And that is how you convert from binary to decimal. A lot simpler than converting from decimal to binary, in my opinion. Okay, so now we are going to move on to octal. And octal is base 8, so remember how we said with any base of n, there are n distinct number of values. So in octal, we have 8 distinct values. So 0, 1, 2, 3, 4, 5, 6, and 7. And why we are going to learn octal and not, say, like hexal, which is base of 6 or something, is because it is easy to convert between binary and octal, and it is quite important to know how to do that. The notation in C and C++ and most programming languages is 0. So if we have an octal number, let's say 0, 3, 5, 7, that means it is octal and not decimal. Another way for humans to represent octal is using the subscript of 8. So we can say 357 subscript 8 is octal representation rather than decimal representation. And so remember, this is kind of similar in that we can use, it is slightly more similar to decimal numbers in that we have more numbers to use, but it is not, because we are missing the 8 and 9 to use in our regular decimal world. So since I said it is easy to convert between binary to octal and octal to binary, is that first you should know that octal, so from 0, 1, 2, 3, 4, 5, 6, and 7 can be represented by binary. Each one of these can be represented by binary. And so 0 can be represented with 0, 0, 0. And the reason why I have 3 zeros is because all 8 of the octal numbers can be represented using 3 binary digits. So 1 would be 0, 0, 1, 2 would be 0, 1, 0, 3 would be 0, 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1, 6 is 1, 1, 0, and 7 is 1, 1, 1. Take a moment right now, pause the video or whatever, to memorize these number combinations. So 0, 0, 0, 0, 1 is 0, 0, 1, so on and so forth, and memorize them, because these 7 numbers, these 8 numbers are extremely important, or at least these 8 binary numbers are extremely important. And so what you would do is, if you had an octal number, so let's say we had our 3, 5, 7 in octal, and we wanted to convert that into binary, what we would do is we would find the equivalent numbers on our chart to the right, to the left here, and we would just insert the binary equivalent. So we have 7, and 7 we see is 1, 1, 1, so 1, 1, 1. And then to the left of 7 we have 5. We see 5 over here is 1, 0, 1, so we add 1, 0, 1. And then we have 3 to the left of the 5. And 3 we see is 0, 1, 1, so 0, 1, 1. And so what we have is 1, 1, 1, 0, 1, 1, 1, 1 in binary is equivalent to 3, 5, 7 in octal. And so if you wanted to convert from binary to octal, so let's have 1, 1, 0, 1, 1, 1, 1, 1, 0, 0, 1, 0, 1. I just totally made that up. What we do is we would start off with the rightmost 3. We're going to take a combination of 3, and we're going to divide our binary number into groups of 3. And we're going to do so until we cannot do it anymore. And then what we're going to do is we're going to look at our chart, and we are going to find an equivalent number in octal that is represented in binary. So 1, 0, 1, we can look at our chart and we see that it is 5. Then we have 1, 0, 0, we look at our chart, we see it is 4. 1, 1, 1, look at the chart, it is 7. 1, 0, 1 is 5 again, and 1 over here is a lone 1. What we can do is, if we have a lone number, or if we have 2 numbers here, so if we had like a 0, if we had a 1 here, what we do is we just add zeros to make a group of 3 again. So if this was just 1, we'll have 0, 0, 1, and 0, 0, 1, it is 1. So our number over here, our gigantic mess, is equivalent to 1, 5, 7, 4, 5 in octal. Okay, so now let's talk about some examples, converting octal to another numbering system. So let's say we have a number 256 in octal, and we, in your course, you may be asked to convert it into binary, and then you may be asked to convert it into decimal, and they may even ask you to convert it into hexadecimal, which we'll talk about in the next slide. So, of course, there are methods of converting directly from octal to, say, decimal to binary and to hex. What I like to do is not really learn new methods, but instead we're going to use old methods that we already know to do the conversions, to make our lives easier by not learning as much. However, what we sacrifice is time. So simply what we do is we always convert our octal numbers into binary. So in our case, we have 256, and in octal, we immediately convert it into binary. And then from binary, remember how we talked about how to convert binary to decimal? That's exactly what we do if we are asked to convert octal to decimal. And so we have an intermediate step of converting octal to binary first. And then on the off chance that your professor or teacher asks you to convert from binary to hexadecimal, you can do that as well. And I can show you how to do that in the next slide. So let's do that. Let's do that as an example. And let's just review each corresponding hexadecimal number in binary. So 0, so octal here, and binary over here. And so 0 in octal corresponds to 0, 0, 0 in binary. 1 corresponds to 0, 0, 1. 2 is 0, 1, 0. 3 is 0, 1, 1. 4, let me put the arrows here. 4 is 1, 0, 0. 5 is 1, 0, 1. 6, 1, 1, 0. And 7 is finally 1, 1, 1. And remember how I said this is an important set of numbers that you should remember. This is something you should memorize. And in octal, it's the same as decimal, so 0 in decimal is a 0, 0, 0 in binary as well, and 1 in decimal is the same as 0, 0, 1 in binary. So that makes everything simple. So again, remember how I said you correspond each number, each digit of the octal, you find it on this table that we just created, and we just take the binary equivalent and substitute it for the digit. So what we do is we take a look at the rightmost digit, so 6, and we find the binary equivalent of 6, which is 110, and then we take the binary equivalent of 5 and we append that to the left of it of 110, so 101, which is a binary equivalent of 5. And finally 2 is 010, so 010, and that is the answer. So 256 in octal is equivalent to 0101011110 in binary. And then remember how we said we talked about how we can convert from binary to decimal. You can then convert decimal. And that is what I would do if you're a professor or a teacher or you're asked to convert from octal to decimal, is that you take this intermediate step of converting into binary first and then to decimal. And that's what I would do. However, there are a method to convert directly from octal to decimal, but I'm not going to cover it here. Okay, so we talked about octal, which is base 8. Now we are going to move on to hexadecimal, which is base 16. That means there are 16 distinct digits in our numbering system for hexadecimal. And if you realize, we're going to use 0 through 9, which we borrowed from our decimal system. And then you will realize that there's only 10 digits in our decimal system, and since hexadecimal is base 16, we have to have an extra 6 digits, and that is where we are going to borrow. We're going to borrow from the alphabet. We're going to borrow the first 6 digits from the alphabet and use that in our hexadecimal system. So we are going to have all the digits from 0 to 9, as well as A, B, C, D, E, and F. So this is from the alphabet. Alright, so why are we going to learn hexadecimal? Just like octal, it is very easy to convert between binary and hexadecimal, which is shortened to hex. So when you hear hex or hexadecimal, they mean the same thing. And for notation-wise, C and C++ use the pre-OX, so a number such as 0x A to C or something is a hexadecimal number, and then there's also the subscript that is added to the number as well that indicate that it is hexadecimal. So let's talk more about how it is easy to convert between binary and hexadecimal. So the reason why is every single binary number has an equivalent hexadecimal number, similar to our octal numbers. So instead of 3 digits, for hexadecimal you need to use 4 digits to represent each number. So let's put hex on the left and our binary equivalent on the right, and we'll probably need 2 columns for this, so hex and binary. And so remember, we've got 16 different combinations, so hex that goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. And so we need 4 numbers to represent each hex number. So in binary, so we need 4 binary numbers to represent each hex. So for 0, that is simply 0, 0, 0, 0, the same as decimal. For 1, it's 0, 0, 0, 1, and for 2 is 0, 0, 1, 0. And as you see, there is somewhat of a pattern. It's the same as all the way up to 7. It's the same as octal. So 0, 1, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 1 for 4, 5, 6, and 7. And for 8, it is 1, 0, 0, 0, 1, 0, 0, 1 for 9, 1, 0, 1, 0 for A, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. And if you see, it actually corresponds from 0 to 16 in decimal. So 0, 1, 2, 3, 4, 5, all the way down to 16 in decimal as well. So now I write all that down because it is really important as well to learn the hexadecimal equivalents of binary. So from 0, 0, 0, 0 all the way to 1, 1, 1, 1, you should memorize what each one is. And so what you do when you're converting from binary to hex and hex to binary is that you just look at the conversion. So if you had a binary number, so over here we're going to do binary to hex, and then on the right we're going to do hex to binary. What we're going to do is, if we have a number in binary, say 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0. So what we do is we divide it into segments of 4, starting on the right, and we continually divide it until we cannot do so anymore, and then the final 4, we add zeros preceding it to make it into a chunk of 4, and then we find the hexadecimal equivalent of the binary. And so 1, 1, 1, 0, we can look at our table over here, and we realize that 1, 1, 1, 0 is E. So E corresponds to 1, 1, 1, 1, 0. Then we have 0, 1, 0, 1, which corresponds to 5. So 5. 0, 1, 1, 1, 1 corresponds to 7, and then 0, 0, 1, 0 corresponds to 2. So our binary number over here is equivalent to a hexadecimal of 0x275E. And then similarly, if we have a hex number, say 0xAF2, and we want to convert it to binary, we just find the equivalent binary on the chart up top, and we just write the binary equivalent. So 2 would be 0, 0, 1, 0, F is 1, 1, 1, 1, and A is 1, 0, 1, 0. And so our hex number OXAF2 is equivalent to a binary number of 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 0. I was able to do it really quickly because I have actually pretty much memorized 0 through 16. So that's why I say memorizing the chart of 0 to 16 in binary is really important, because once you do, you can quickly convert from binary to hex and hex to binary. Again, similarly with Octal, they may ask you to convert hex to decimal. They may ask you to convert it to binary, and they may ask you to convert it to octal. So, again, my advice is the same to you. Convert it first to binary, so hex to binary first, and then we had our versions, we had our rules to convert binary to decimal, and we had our version of binary to octal. And I think that is the most easy way to memorize how to convert hex to any other numbering system, is converting it to binary first and then to decimal or octal, depending on what is required of you. However, there are methods converting hex directly to decimal and vice versa, but we won't really talk about those. They're not, I don't think they are quite that important. I think our mainstay tool is going to be hex to binary, and from binary to decimal, and any other octal. So let's just do a quick example. So let's say we had O, X, B, C, 6. All right, and then we want to convert it to decimal and octal. So we're going to do all of the conversions. So what we do is we just take our hexadecimal number, and we find the equivalent digit, equivalent binary digit for each hex digit. So for every hex digit, so for O, X, B, C, 6, we find each equivalent binary combination for each digit. So for 6, we know is going to be 0, 1, 1, 0. For C is going to be 1, 1, 0, 0. And for B, that's going to be 1, 0, 1, 1. Okay, so now we have a binary representation of our hexadecimal number. And then we can convert our binary number to decimal and octal. So remember how we said for binary to octal, we just divide it into groups of 3, and then we can convert it easily. Well, the same thing happens here. So we divided our binary into groups of 3. So it happens so that it divides nicely. So 1, 0, 1 is 5, remember. 1, 1, 1 is 7. 1, 0, 0 is 4. My apologies, it actually doesn't divide nicely. Let me see. So let's start from the rightmost. So 1, 1, 0 is 6. 0, 0, 0 is 0. 1, 1, 1, 1 is 7. And 1, 0, 1 is 5. So it seems like it divides nicely. And so our octal representation of our hexadecimal is 5706 in octal. And in decimal, the same thing happens. What you do is you multiply by the corresponding power. So here we will be multiplying by 2 to the 1, and then adding by 2 to the 2, and so on and so forth. I'm not going to do that because that's calculator work, and I'm sure you can figure it out.